evolution of woody vegetation clearly rates as one of the major milestones in Earth history for its impact on biodiversity, Earth's geomorphology, and the chemistry of the soils, atmosphere, and ocean. Some of these are pretty clear-cut. Plants affect biodiversity, for example, by creating a highly structured land surface as well as a rich supply of food. Geomorphology is also affected since the soils produced by chemical weathering end up mantling Earth's surface, muting slopes and valleys, and delivering fine-grained sediment to the oceans. Soils are themselves a rich cradle of biodiversity, particularly in their microbial and cryptic Metazoan biota, and they end up being a major site of carbon storage, chemical weathering, and gas exchange with the atmosphere. Here we consider another consequence of land plant evolution, namely the effect of plants on Earth's carbon cycle. Land plants are sponges for CO2 since they take up carbon dioxide in photosynthesis and use that energy to make sugars and wood. One of their big impacts on Earth's climate system is their role in accelerating carbon burial. The formation of coal in particular has the consequence of both drawing down carbon dioxide and increasing the delivery of free oxygen back to the atmosphere. Land plants therefore have a similar Earth system effect as plankton did on carbon burial back in the Paleoproterozoic. The key reaction is that wood and oxygen form a balanced reaction with carbon dioxide and water. For instance, photosynthesis uses CO2 and water to make wood and free oxygen, and the reverse is true when that oxygen is used to burn wood, liberating carbon dioxide and water back to the atmosphere. If the wood is buried, the free oxygen is not burned or used by some organism to eat wood or other plant material, and so the oxygen remains in the atmosphere. The consequence of organic matter burial is therefore an atmosphere richer in oxygen and poorer in carbon dioxide and subject to global cooling. All this suggests that when plants first started to make abundant wood in the form of the progymnosperm Archaeopteryx about 375 million years ago, we might expect glaciation to ensue. Indeed, that's just what happened. Glaciation starts in the late Devonian and continues through the Pennsylvanian and Permian. There is abundant evidence of these glaciations, even far from the ice. For example, there are the Pennsylvanian cyclothems, a series of expansions and retreats of the oceans over the mid-continent of North America as sea level bobbed up and down with the growth and decay of polar ice sheets. The cyclothems commonly show cycles from coal swamps formed during times of maximum ice growth on the pole when sea level is low that pass upward into shallow marine carbonates as the ice sheets wane and sea level rises. Modeling shows that just the burial of organic matter in Paleozoic forests reduces atmospheric partial pressure of carbon dioxide by around 600 to 900 parts per million vapor. This is a big swing in the greenhouse effect. During the recent glaciations, by contrast, CO2 swings from maybe 180 parts per million in the glacial period to the present value of 410 parts per million. The point is that a 600 to 900 parts per million drop is really big, plenty to get glaciers moving. Now, plants do other things besides just bury wood and make coal. They also accelerate the weathering and chemical transformation of minerals, and those weathering products fertilize the ocean. Here, the relevant reaction is that of carbon dioxide, when reacted with silicate minerals, is in a balanced reaction with calcium carbonate and silica. The weathering of silicates draws down carbon dioxide and produces carbonates and silica as runoff to the oceans. In turn, metamorphism of silica and carbonates produces silicate minerals and carbon dioxide. What weathers the silicates? Well, the guilty parties are plant roots and the chemical reactions of humic acids from the decay of plant remains. Plants are really good at weathering rocks, both for intentional and unintentional reasons. First, rootlets secrete acids that directly attack mineral grains, and they are aided in this by those fungi mentioned in the last lecture. Organic leaf litter not only decomposes to form humic acids, but also is very effective at holding water in contact with mineral grains, thereby accelerating weathering. The clays formed by plant weathering also assist in holding water, thereby increasing mineral-water contact time and the efficiency of mineral breakdown. Not only that, but plants recirculate water via transpiration out of their leaves and increase rainfall over forested areas. once again increasing water mineral contact time. Finally, roots and associated soil biota biodegrade the soil, speeding up physical breakdown of minerals. For instance, a tree falling over in the forest will often pull up great masses of rock and soil in its root system, mixing the upper soil layer and exposing fresh rock to attack by plants. So here is the punchline. Experimental studies show that trees enhance weathering by factors of 3 to 10 times over bare conditions. People have actually made study plots where pines were planted, or not, in sand plots where all the moisture was captured and measured via a series of subterranean pipes. These experiments show that fluxes of calcium, magnesium, and silica from pine-covered soils were 10 times higher than that of nearby barren plots. Just think of that. Before plants sent their tendrils out on land, the weathering rate was at least 10 times less than it is now. That is also 10 times less nutrient delivered to the ocean and probably 10 times less photosynthesis and production by everybody in the ocean than now. If molecular clocks are right, then this land plant revolution started about the time the Metazoans were starting their planula-like radiation. But that contribution of weathering products from lichens and maybe a liverwort or two was nothing compared to what came with woody plants. Indeed, the story is hardly over when forests come along, because some plants that are relatively young are exceptionally good at very specific types of biochemical transformation. For instance, the lowly grasses are first rate at extracting silica from soils. Grasses dumped that silica into the ocean when grassland spread over the continents 30 to 40 million years ago, probably contributing to the rise of siliceous diatoms as primary producers in the oceans. Plants are massive biochemical and biological engineers. Next to the cyanobacteria and their contribution in oxygenating Earth's atmosphere 2.5 billion years ago, land plants are probably next for the sheer scope and magnitude of their impact on Earth's ecosystems, chemistry, and planetary metabolism.